Hello, everyone. Welcome to our core protocol sync. It has been almost a month since we have it, since we had it last time, due to holidays and the offsite and everything that was happening. However, we do have some updates from our team that we'll be sharing today and also discussing plans for the immediate future. And I'd like to start as usual with Shamil.
Sure. Last week we had a major update from the GSM side, from the networking side. We finally merged our long-awaited pool model PR for the academia. I will remind you what does it mean. That's basically the previous version. When we have new pieces in the system, it pushed all the new pieces through the network to other nodes or farmers or even Bootstrap now to all the participants of the DSM. But now, currently, on the pool model, when the new pieces arrives, let's say from the node side or from farmer side, the peer only announces that it has this piece. It's a small message across the network, and other peers could opt in and pull this new information from the network. So we changed from publishing large piece, let's say 32 kilobytes now, and change it to only announce a small, let's say 100 bytes message. So we expect to have a much better networking experience. So I'm very excited that we have it now, and we will test it in our next testnet. Also, last week I had a small update for that pool model PR as a separate PR. It was requirements from Nazar. He asked me to a little bit improve storage for this provide announcement records on the node side. It was in memory, and I reused some code from Farmer and made it persistent. It's currently under review. Also, I started my next task. It's next part of the block importing PR, and um, I will basically make Node optionally sync from the DSN on startup. And it requires some refactoring, and I made a PR with the preparation for this task, which is move the common shared code of piece receiving from the farmer to some separate location. Currently, it's a networking crate. It will allow to use basically similar code, both using nodes and farmers. So this just prerequisite PR. So that's it. And my next piece of work would be just proceed with the block importing from the JSM. That's it.
Yeah, pool model is really promising. Without it, I was testing and I was regularly hitting over 100 megabits per second of upload because I was archiving and publishing pieces, and that's all needs to be uploaded, even though many of the nodes already had it. So yeah, that's really good thing. Let me share my updates. There aren't many that are notable, but there are a few.
Hey, one question. So this pull model means you send advertisements first, is it? Is that what we call pull model?
Sorry, could you repeat?
Pull model, does it mean like first we send advertisements and then other nodes decide to download if they don't have it?
Yes,
Is that?
and yes, exactly. And the decision it will calculate that hash for this piece and compare to local peer ID by academic distance. If the distance within our boundaries, then it will upload it. And also the other limit would be the size of its local cache. So it's a new piece is close enough to this piece and the cache is not exceeded, that it will download it to itself. If not, it will just skip that event.
Yeah. On my side, there were a few discoveries after reading peer-to-peer code. The first one was related to the fact that we store our peers in the database for persistence. So we can use it after restart or when we are having too few connections. We didn't actually check that those addresses that we are trying to dial in that case are actually global if we have restricted ourselves to that. This is like a part of it. The other part was done by Shimil last week, I believe, that actually has a wrapper around transport that physically prevents to connect to those local addresses. That's something that we had our servers banned because of. And I think we'll need to send a similar pull request to Substrate itself as well, because it doesn't have, I believe, protections in all cases. For instance, when you have one peer that has announced the DNS record, and then during connection, you will resolve it and you will get an IP address. That IP address can be local, potentially. So that was a relatively simple one. This one was actually a request from the SDK/CLI side. They wanted to have a proper sync status of the node. It
Did I just lose another version?
No, I did as well. Let's see if you can message. He's not responding on Slack either. Maybe we can move on and come back to Nazar. Who's normally after Nazar? Who's got an update to? Ved or Lu Chang, do either of you have anything for protocol?
Nothing on my end. I'm just here to get more info from last week that I was missing. But nothing from my end.
I'm sorry. My
Yep.
computer didn't work to cooperate. It freezed me.
We started moving on without you, Nazar, but I'll let you jump back in and take over.
Okay. Yeah, so basically the thing with the CLI and status sync status check was that in some cases when we have peers and we already started downloading some blocks from them because they have some blocks, but they are not synced yet. So we don't know if what they see as the tip is actually the tip. And in that case, the node was confused and was reporting idle. Right now, we've introduced a new status which is pending, which in that case will just say we are pulling something, we are importing something, we don't know if that's the correct chain yet. So that was the change for the CLI and SDK. The other important thing was related to DSN. When we are pulling pieces on the farmer side, we didn't actually check if those pieces belong to the chain. Now we do. And also we check and ban peers that return incorrect pieces. So essentially, if you have mixed set of nodes on the network that are part of different chains, they will partition into different subnetworks, essentially. So for that, we expose the method for banning peers, and then instead of returning just values, we return peer record, which has a peer ID from which we've received the information, so we can ban them if they return a piece which belongs to a different fork, basically. So with those things and the things that Shamil did, I think we should be in a pretty good shape for the Gemini 3C. How it actually works, we will see soon enough. Any questions about that? Okay, I believe Luchain was sharing some updates, right?
Oh, I was like about to. So actually, no like solid updates on the core protocol. Just a few things like from the milestone 3 reviews from Pretty. One thing I think is like we discovered when I think flow on the receipts verification where you can provide an arbitrarily larger vector to like exploit something, because we have a check on the receipts, like to ensure the receipts are consecutive, and in which we did an iteration on this vector. So it makes sense to like add a constraint on the maximum number of receipts which can be contained in a bundle. So this is one thing. I'm just not sure like what's the proper value for this like max receipts in a bundle. Any ideas?
Isn't it already restricted by the size of the transaction implicitly?
Well, yes, but that could be huge.
Okay, I guess I'm not fully in the context. I'm just thinking that iteration is not that expensive in general. If you just like go through it, if you're like doing some computation, that maybe.
Well, maybe I'm not benchmarking anything, so it's just a theory. Theoretically, like it makes sense.
Okay.
Another thing is like mentioned the arithmetic operations. Like I think we probably need to define some more clear rules on those like arithmetic operations. So
Yeah, in general, I'd like to not allow any regular arithmetic at all. So like every single mathematical operation should be checked. And also there are some things that concern me when we have one type and then we write as another type. In most cases, that is actually like correct, but probably not 100% cases. So when it is possible, like when we have, let's say, U32 and we want to have U64, I'm usually writing U64 : from that other number. So it will fail to compile if the types change. But we do still have U size in some cases. And it's really awkward with try into or try from, but you probably should do it. So basically, if possible, we need to have some kind of clip-lint that will ensure we will provide proof for every single operation, explaining why it will not overflow, underflow, or like divide by zero, whatever might happen.
I just feel that if we we plan to add like use checked operations everywhere, the code will probably look ugly.
It will, but we are working in a domain where this is critical.
Okay. So I think the current consensus is to try to use checked operations, like if possible.
Yeah, I'd really like to avoid just saturating arithmetic because it might hide problems. We should really like consider every single case whether it makes sense. In some cases it does. In some cases we should just panic instead or like return an error or whatever.
Okay. So yeah, another thing like will affect the co-protocol thing is the proposal I mentioned, like on the codomain nodes management. So the idea is to like the domain builder needs to upload the runtime codes onto the like consensus chain upfront, and until this like runtime code is confirmed or is included on the consensus chain, these like new runtime code starts to take effect. It's kind of this idea.
So this is for core domains, right?
Both system and core domain, every domain.
Yeah, I'm just thinking, how will we verify that? It seems like we need some kind of object mapping
Yeah,
here
so
we can prove.
So So for the system and the codomain, the color will be root, right? For the open domains, the color will be the maybe domain creator, or maybe even the root is allowed. And in that case, the domain builder wants to update the domain code. It will need to provide a storage proof to verify, to prove that the color is the allowed account to update this runtime code, and this matches the state on the system domain. We have the system domain the root on the consensus chain, so we can verify if you can provide a storage proof.
Yeah, what I meant is that we do not have any reference to what kind of objects or data we upload in the runtime. So you cannot prove that this runtime with this hash was uploaded 2 days ago or something like that. At least not yet.
Sorry, what's I don't quite get what's the
Okay, maybe I misunderstood how we want to implement it. So if we want to upload the runtime first, and then we say runtime with this hash needs to be applied at this height, then we need to prove that that runtime was actually uploaded before. And you don't have any reference to what was uploaded in the runtime right now.
well, on the domain side, if this extrinsic is included on the consensus chain, we can find corresponding event in a block. We consider it's uploaded, it's stored on DSN. So if it's really successfully stored on DSN, that's on the DSN side. It's expected to.
Yeah, the challenge there is that you can prove that a transaction hash was included in the block. You cannot prove that data within that transaction was actually some hash, some other hash. So that's the challenge that object mappings were tackling.
But nope, I think you probably mix a few things. So on the consensus side, if the farmer only needs to verify if a color is allowed, if the sender of some extrinsic to upload this domain code is allowed.
Oh, I see. You just want to have a special transaction for updating runtime.
Yes.
I see. I remember Jeremiah was talking about an alternative before where you first upload just like a blob with the runtime, and then you can reference that blob in other things. So let's say you have 10 domains, which are public domains, open domains, which use the same runtime. You could just reference the same hash. You don't need to upload it 10 times. So that's what I assumed.
Okay, that's an optimization. Yeah, we can do that. Yeah.
This is close what Polkadot does, if I'm not mistaken. They have some runtime pre-image concept.
Yeah, they have.
So yeah, that's my updates on this side.
Okay. Rahul, did you already share updates?
Yeah, so my main update, I was working on the profiling for the C implementation of the KCG library, and I have some preliminary numbers and preliminary findings. Last week I also managed to run I added a new benchmark. I managed to run it on both my MacBook Pro M1 and also the x86 machine that I got from Nazar. And I found surprisingly the M1 Pro is outperforming the AMD x86 machine. It goes anywhere from for small polynomials, it's about 10% or 20% faster. And when you go to really large polynomials like 32K points or 16K points, it's almost 50% or 60% faster. So I was quite surprised to see that. I was thinking the AMD would be faster. given that M1 has been around only first generation, right? So, but it's pretty impressive. And I also identified some other bottlenecks in the C implementation. Today I'm going to work on like some changes. I'm going to experiment with some improvements I have in mind. By end of the day, I will update with the new numbers if it improves things. That is mostly it. Apart from that, I've been mostly working on like preparing for the consensus changes with the Jeremiah. And mostly around like I was reading some research papers around from David Say and his team. This is mostly around like proof of error of time and the Prism implementation of the proof of stake and so on. So this week I'm meeting with Jeremiah a couple of days in Hacker House. So hopefully I'll have a better plan by end of this week about what I'll be doing next.
I'm just curious, how complex is that C library? Because the underlying BLS implementation actually has Rust bindings. I believe it's called blasters. So maybe we can like write the same thing in Rust on top of that Rust library, so don't have to deal with such a low-level C
Yeah.
quite as
So
much.
the C library it's pretty nicely written actually. It is like a wrapper around the BLST crate. Or in fact, the BLST is mostly like it's already FF5 around C functions from what I read the code. They mostly call a bunch of C stuff. So I think it may be easier to just modify the C library so that, and then we can add FF5 on top. Because otherwise it'll be like a lot more work if we have to re-implement the whole thing ourselves using BLST.
I see. It's just that if you want to go C route, we need to like write all these wrappers and compile things in platform dependent way and stuff like that. If you just have a crate, it's much easier, but
Yes.
there is a
So
lot of work in the other place.
yeah, so I think my current idea is like, let's say if I can get some decent numbers out of the CKCG, we can just add some FFI bindings on top. Because from what I see, we only need like 3 or 4 APIs, high-level APIs. For example, create a commitment, and then create a witness and kind of thing. Like we only need like 3 or 4 high-level APIs. I think that should be easily addable on top of the CKCG if we have like decent performance out of it. Yeah, I noticed like we do a lot of, or rather the CKCG, right? It's written in a very generic manner. For example, polynomial divisions and so on. It's written in a very generic manner to handle all cases. We don't really need a lot of that. If you kind of simplify that thing, right? That's the thing I'm going to do today. I think that will cut down a lot of time.
I mean, we also don't want to maintain forks of those projects necessarily, which is another kind of maintenance burden.
Yeah, that's true. Yeah, let's maybe sync up. I'll try to publish a PR of the stuff I've done to improve things by maybe when I'm done today, hopefully. Let's go through that and then decide what we want to do. If you want to use that or re-implement the whole thing, maybe we can take it from there.
Okay.
Yeah, that's it for me.
Yeah, after working with Daria a little bit on this stuff, it seems like there is not that much API surface on top of BLS that we actually like need to implement to get things working. So maybe we'll see.
Yeah, so I think the CKCG uses a lot of BLST stuff for like even low-level things like the field point arithmetic, and then all the G1, G2 arithmetic and all that stuff. So they already have wrappers for everything. If we want to do everything on our own, we'll have to pretty much copy paste a lot of that stuff from CKCG. Yeah, so yeah, we'll see how it goes.
Okay, makes sense. Daria, what about your updates?
So I could give you a little overview of what is the latest iteration of the consensus look like. So basically it still has same ingredients that we have already considered. They're kind of mixed a little differently. The main ingredient that was the biggest part of consensus week 2.2 was the idea of erasure coding, but we are doing sort of unique erasure code of the pieces for each farmer. So that is something that was Chan's idea. It doesn't seem like any other project is doing it, which is a very smart idea, because you can actually do that instead of doing erasure coding the same for everyone. Each farmer has a unique set of code points they extend the pieces on. So that's one ingredient. And the second ingredient is the Chia proof of space. But we are not actually using Chia proof of space to fill up the space like Chia does. We are using Chia tables because they require some memory bandwidths to be computed. So for each piece that we are going to be storing at the farmer, we compute a little Chia table, which I believe is going to be like 4 or 7 megabytes. While and on Chia protocol, there are like 30 gigabytes. So we're computing this little Chia table, and we're using it to mask the piece, to encode it, just by XORing it with
It's
our
like
polynomial
one-time pad.
extension. Yeah, basically. And it's going to be unique for each piece because the table is built on some seed that you give it, and we're going to be deriving a unique seed for each piece for the farmer. And well, that's basically what it does. The farmer downloads pieces, extends them on a unique set of points, XORs them with the Chia proof of space, and stores that. Now to decode, you'll need to generate a Chia table just for that specific piece that needs to decode, evaluate it back on the first points, like from 0 to 2000, to get back the original record, and serve it back. Now, if you want to hear in more details, I could go through the diagrams that we have. If no one else wants to share updates, I could go in more detail.
I have 2 questions, if you don't mind. First, what is the current size of the piece?
1 megabyte we're looking at. However,
Okay.
the thing is, Nazar has some concerns whether the KZG is fast enough for us to handle that piece size. So it may be
Yeah, I'm
reduced.
just worried that we will require too many cores in total in order to be able to archive it within a reasonable amount of time. Like, we don't want to wait a minute for a segment to be created before we can produce the next block, right?
So it may be reduced, but will not be increased, certainly.
So this 1 megabyte is like basically it's a multiple of 31 or something, right? That is the number of points we'll have in the polynomial. That 1 megabyte by.
So that's like one record. Yes, we chunk it into 31 bytes, but we have 256 of those records to deal with, or at least 128, depending on how we approach it, which is quite a bit.
Do we know at this moment what time will it require to decode the piece on the farmer side?
Not yet.
I know.
No.
We
What
hope
will be a rough estimation?
it's like we hope it should be below a second, so it should not take minutes.
Yeah, the Chia table, like the small table, it doesn't take that much time to compute.
I
And
think
then, like,
so.
decoding should also be fast.
The current so the Chia takes like half, like 400 milliseconds for the table like that, but we also want to reduce that because Chia does like 7 tables and compresses them. We don't need all of that, so I will probably have to modify, and we will have to fork the Chia library anyway because they don't allow tables that small in their protocol. So we'll have to do that anyway, and so we can modify the table generation to just do the first pass without all the compression smart stuff that they're doing. So that should be much faster. And then the thing that's going to be taking most time is the KZG, the erasure decoding, because that requires taking those 32,000 points, interpolating a polynomial over it, and then evaluating the polynomial on another set of 32,000 points. That's probably going to be the biggest bottleneck, which again may be reduced if we do reduce the piece size, but we do not have a decision on that yet.
Hey, so
Yeah, and many of these things can actually be parallelized. But on smaller machines, if you assume that you have like 2 or 4 cores dedicated, like Raspberry Pi, you don't have that much parallelism in the end.
hey, so since I've been looking at this last week, what is the order of the polynomial size that we're talking about here? Is it like I remember Daria mentioned 256 points or 255-degree polynomial at some point.
So we have 2 types of polynomials that we'll be dealing with. One of them is the piece polynomial or the record polynomial, which is going to be 32,000 around, if that's 1 megabyte. And another is the segment root polynomial, which is 256.
Okay, so we do have like a case for 32K points in a polynomial. Okay.
That's again given we go with the piece size 1 megabyte. That is the polynomial size. Yes.
Okay. And in all cases, the size of every Y evaluation is like 31 bytes in both cases.
Well, it's actually like 254 bits.
Yeah, I mean, the
so
last
It is
bits.
allowed to be, but
Okay.
we are not using those 6 extra bits.
Okay,
Because
but it's going to be
inconvenience.
32 bytes effectively. For every point is going to be 32 bytes, whether it's 256 points or 32K points, right? Okay. Because that gives me something to work with when I'm doing the measurements. So thanks.
I mean, in some cases, it will be 254 if you are talking about the hashing that we will be implementing. But from the library point of view, whether it's 254 or 248, it doesn't really change the API in any way. We just give it 32 bytes and we assume that at least 2 bits are empty.
Yeah. So, but the thing we are interested in is like 32 polynomial of degree 31 and 32K minus 1. Is that correct?
Mm-hmm.
Okay.
So you want me to give a more detailed overview of the things?
I mean, we have about 19 minutes. If you can do something quick, then sure.
Yeah.
Otherwise, it might be worth having like a separate call for this.
Well, we'll certainly will. I'll probably just scroll through some diagrams that I have and say a few words of each of them. Well, specifically about plotting. So archiving is kind of, well, it didn't change since the last iteration that we had. We're collecting a segment of 128 pieces. For each piece, we interpolate a polynomial. We do a KZG commitment to the data inside that piece, and we store that commitment. So each record will have its own KZG commitment. Now, the second step for the archived segment is we take all of those commitments for the records plus the erasure coded records. We hash them so that they become 32 bytes because otherwise they're too big. So we hash them so they become 32 bytes, and then we KZG commit to them again. This is what effectively is called a Merkle tree, which is like a Merkle tree, but you use the KZG commitment instead of just Merkle hash functions. So we're having 2 layers of that. And to prove that any particular data point, which is like 32 bytes, is a part of history, you will need 2 proofs. The proof that it belongs to a specific piece, and then the proof that this piece belongs to a specific segment. And the segment root is going to be stored in the block headers and in the state, I believe. So that's going to be accessible to everyone. And this way you'll also be able to verify when downloading pieces where they belong to the history just from their commitments. So that's pretty easy. We didn't really invent a wheel here. It's known stuff. The plotting is completely unique. Let me show share. Nope, not this one. So as we have already done in consensus v2 right away, there's not going to be any more max plot size notion. So your plot can encompass whatever space you have on disk. However, it will be divided into sectors. Right now, we're looking at like 1.3, 1.5 gigabyte sectors. And each sector will have verifiably random sampling of pieces from a whole history based on like farmer public key, like sector ID, but everyone will be able to verify that this farmer has to actually store the specific piece in their sector. And so if we're looking at like 1.3 gigabytes, each sector is going to have 1,300 pieces. Next step, what we do for each piece, we derive a unique seed.
Hey, one sec. Could you go to the left in a picture?
Oops.
Hey, so what's in the record? It's like piece plus the commitment or something?
So piece is the useful data, and useful data is what we call record, plus commitment, plus the witness that it belongs to a specific segment.
And that is record. Record is basically data plus commitment plus
Record is just the data. Piece is record plus proofs.
This it says record here, that meaning that we will be encoding just the actual data. We will not be like encoding the commitments we'll just be storing them apart to be able to verify later. But all of this chia encoding and extension are going to be happening on the raw data without the commitment and the witness. So that's why I say it record. I just thought having piece on both sides will be confusing, but it's confusing anyway. Okay, that's a nice comment. So after we download from DSN all of these pieces, records that we need to store, for each of them we derive a unique seed and a unique chia table. This should actually be done sequentially, so you don't do all of them at the same time. We just do piece by piece. So this whole rest of the workflow is going to be sequentially for each piece. Next, we have to derive for each farmer a unique set of points that they will have to evaluate the polynomial on. And the way we do that, from the same seed, we derive some starting index, which is going to be, because the seed is unique, is going to be unique for the farmer. And we try to query this chia table for a proof of space, which is basically just treat it as a black box. If you query this table for a specific value, it's either going to give you a value back or it's not going to give you a value back, which happens with some probability. So we will have some of the indices missing, but that's technical detail. So this proof of space might be a little larger. And we will have a bit string here that indicates whether we did manage to get a value from the table. It's going to have a 1 or it's going to have a 0 if we did not. And this will indicate for us the points that we have to evaluate the polynomial at to get the unique erasure coding from the farmer. And so once we got for a specific record the set of indices for the extension, we interpolate the polynomial over the original data, and we evaluate this on the set of indices that we have just gotten from chia. And then we do so sequentially for each one of them. And because generating the chia table takes memory bandwidth, and looking up also takes some, this is how we prevent on-demand computation or farmers faking space by computation, because this we're treating chia basically as a resource-bound and memory-heavy function, which should be ASIC resistant for different as in consensus V1, because it's bound to memory and not to the CPU cycles. And for audit and for extraction, we will only have to derive one single table for one single piece that we're looking at. So that's going to take way less work than to actually plot the whole thing. So back to what we're doing, we have interpolated a polynomial over the original data, and for each piece and for each farmer, we have extended it on some specific unique set of points. After we've done that, we take the proof subspace, again from the chia table, and we XOR them with every single chunk, well, where the chunk is 32 bytes of this extended erasure coded extension. And after we've done that, we already have an encoded piece. These X's just show that some of the indices may have been missing, but we don't actually have to store anything here. We'll just have a bit field that will be indicating which indices we actually did evaluate on. And to mix things a little bit, what we do, we are not going to be writing the pieces sequentially as they were. We will be taking the chunks from each piece and basically realigning them column by column, and skipping the ones that the points that did not evaluate. So it's going to be reduced in size. Well, not really reduced in size. How do you say? It's going to be dense. It's not going to be sparse with this missing points. So basically, each of these buckets is going to have one chunk of every piece that we have. It's going to have, so for example, this S bucket 1 is going to have the first chunk, the first piece, the first chunk of the second piece, the first chunk of the third piece. So that kind of mixes things up. And then we write them to the plot, and that's going to be our encoded sector. So what we're going to be storing in the sector are going to be these buckets, which are basically columns of chunks of 32 byte. Each of these buckets is going to be around 32 kilobytes. Plus, we're going to be storing this bit strings indicating the indices that we have been evaluating on, so we can decode correctly the pieces when we have to serve them. And we're also going to be storing the original KZG commitments from the archiving so that we are able to verify whether the decoding was done correctly, and that we are able to prove in the consensus that our solutions are correct. Now, at the audit phase, what we do is for each of the sectors that a farmer has, so if I have, whatever, 15 gigabytes, I'm going to have like 10 sectors. For each of the sectors, we are going to pseudo-randomly derive one bucket of these to read on. And each bucket has chunks from every piece. So we're going to read for each sector just one bucket into memory, which is 32 kilobytes. And we are going to scan it for a solution, which is a chunk that is close enough at our solution range, just as it was before. And if we do find a chunk that is close enough to the solution range, we have to do all the work back just for this one specific piece that this chunk belongs to. So we have to get the chia table, get the proof of space for the specific, oops. Lucid scrolling is really awkward. So to decode this back, we have to take the indices that we have been evaluating on, look at the chia table for the proofs, which are our encoding keys, XOR it back, like here. And after we XOR it, we're going to have the evaluations, which are the unique erasure coding. And we will have to interpolate the polynomial, and then we'll have to evaluate it back on the original set of points. And then prove that this chunk that we had is actually a part of history. It does sound complicated, I think. Jeremiah says it's a really simple scheme, and actually the ingredients are just two. It's a Qi upload table as encoding and the extension. But if you go into the actual nitty-gritty, there are a lot of details and things you have to be.
We are a little bit biased in terms of complexity.
Yeah. So that's kind of it. I will be having more diagrams for like exactly extraction, and there is also another diagram for the whole consensus thing, but that's basically the design that we're looking at, and we're still just polishing out the details on what the sizes are going to be, which is probably going to be required some implementation and testing. What is actually feasible to do in a split-second slot.
Will we have some ready specification in order to prepare for your very simple presentation?
So in Consensus V2, there is a new specification in Consensus video folder. Let me show you 1 second.
It's called 2.3 version.
Yeah, so I have cleaned this up. As you can see now, there is way less than there were in this folder, and it is now V2.3, but it's super detailed because it's supposed to be the implementation guide, and it has the open questions in the notes. And so, yeah, if you want to read it, you're free to do so, but it's enormous. So, yeah.
So one question, like you mentioned, like a 3-second budget, right? Could you talk more about like what is the time budget we have in mind? How much
Well,
time do we have?
I said split second.
Oh,
So
split
it's,
second.
yeah. And maybe Nazar can talk more about it, what the desired numbers are.
Yeah, so there are different parts of the protocol. So when we are talking about auditing, we just have a second to make an audit, create a proof, produce a block, and ship the block out to be the first one. So that's like a very time sensitive thing. The other thing is when we are doing archiving, it's kind of similar because if you are doing archiving, you are increasing the height of the blockchain, and at minus k confirmation depth, you have to archive the block. And if that archived block results in new segment being created, you need to do the archiving process, which also takes some time. The challenge here, at least the way we have protocol right now, is that the basically the header of that new segment, we call it root block, has to be included in the very next block on chain. So you cannot produce the next block until you finish the archiving process, which again makes it time sensitive, maybe to a less degree, but still. So with block being on average every 6 seconds, do the math, how much time we have. We can potentially tweak it. Like we can say, we don't include the root block on the next block, we include it on the like plus 100 blocks, but then it actually impacts the time it takes for someone to upload data onto the blockchain, and then being able to query it means that like verifying that the data is actually part of the blockchain. We don't really want to extend that unnecessarily, so we have a lot of like trade-offs here in terms of the performance, usability, and other things. Okay, I think we are about at time. Thanks everyone on YouTube for watching. I hope this short presentation from Daria was helpful to have like a at least intuition what the consensus looks like. We'll certainly be sharing more updates about that soon. And we'll see you in 2 weeks, I believe.